Let's imagine for a second that we just invented a shrink ray. This machine has the capability to shoot anything down to a mere fraction of its original size, even humans. Sounds pretty cool, right? At an inch tall, imagine all the interesting stuff you could do. Riding small animals, sneaking into your favorite sporting event, and even if you were small enough, you could get up close with human anatomy. But is this really feasible?
Unfortunately, this type of scenario would not be feasible. Us humans wouldn't live very long at that size. The same forces and physical properties which govern our daily life now would take on extremely different forms at such a small scale. Let's dive into this a little bit further.
Let's say that you start 70 inches tall, and then you shrunk down to 1 inch. You have decreased in size by a factor of 70. The surface area of your body is measured in length squared, and thus has decreased by a factor of 70 times 70. This is about a 5,000-fold decrease in your surface area. However, the volume your body is measured in is length cubed, and has now decreased by a factor of 70 by 70 by 70, giving about a 350,000-fold decrease total. The surface area to volume ratio of you is now enormously large. Since animals lose a majority of their heat through their surfaces, you will begin to lose heat at an exponential rate, and you will quickly go into hypothermia. You'd have to consume a large amount of food and have a superhuman metabolism just to keep your body heated.
Somehow you survive that rapid heat loss. Whew! However, a larger surface area to volume ratio means that you'd also be losing water at a proportionately larger rate. To remain alive, you would have to drink well over your body weight in water every day. Additionally, at this scale, surface tension forces are much greater. It would be almost impossible to take a drink of water without being immersed within the water drop itself. This will also make taking a bath extremely difficult. At small scales, liquids have a low Reynolds number, which means they act in a more viscous, laminar fashion. With this type of flow, it would feel like you are taking a bath in molasses and definitely not being able to adequately move around. You may just be stuck in there forever.
Many of your senses would be significantly altered as well. Let's examine your speech. Humans create sound by vibrating their vocal cords. Vibration is directly proportional to size. Thus, smaller vocal cords in the smaller you would vibrate at a much faster rate. Faster vibration rates translate into higher pitched sounds, so your voice would be turned into inaudible, high-pitched squeaks. Your hearing will follow much of the same pattern, as we detect sounds by the vibrations of the cochlear liquids in the inner ear. Thus, you wouldn't be able to adequately hear all the sounds around you, and those which register within your brain will also be extremely high-pitched. As if that wasn't bad enough, you probably wouldn't be able to see very well either. The pupil in the center of each of your eyes will be significantly smaller, which wouldn't let in enough light for the formation of clear images, and your field of vision would be extremely narrow. If you are shrunk down enough that your pupil has a diameter of about half a micrometer, then more serious problems would arise. This is because the wavelength of visible light sits on this scale, so you would no longer be able to focus incoming light. The world would just look like a blurry haze.
At such a small scale, objects will begin to look and feel differently as well. Everyday objects that we view as having smooth surfaces are actually pretty rough when you get close. For example, if you were to proportionately enlarge a billiard ball to match the diameter of the Earth, it would have higher peaks and lower valleys than that of Earth. Earth's highest mountain, Mount Everest, sits about 9,000 meters above sea level. However, a billiard ball the size of Earth could have mountains that reach over 28,000 meters. That's over 3 times the height of Mount Everest.
You are now navigating your world in desperation of food and water, and without having adequate sight, hearing, or speaking abilities. Now imagine a gust of wind comes by. Because of your very small mass, you might be propelled into the air and transported a very far distance away. This could be advantageous for quick travel purposes, but you wouldn't be able to control where you're going.
Being shrunk down so small doesn't sound so great anymore. I don't know about you, but I'll continue being an average-sized human being. However, we know that some animals on Earth are able to live at these small scales. How are they able to do this?
Let's examine the smallest warm-blooded vertebrate, the bee hummingbird. This hummingbird is comparable in size to a honeybee and is lighter than a penny. The bee hummingbird is subject to many of the specific challenges that we have previously discussed. For example, it needs to eat twice its body weight in food, which translates into visiting about 1,500 flowers every day. It has a specialized long beak and straw-like tongue in order to get as much nectar as possible from the flowers. Additionally, the bee hummingbird must drink 8 times its body weight in water. The scavenging for food and water expends a large amount of energy. So how does the bee hummingbird maintain its internal body temperature?
These creatures have a very specific adaptation which allows this. At night, they switch into something called torpor mode, which produces a short-term decrease in body temperature and metabolic rate. This allows the bee hummingbirds to expend enough energy during the day to search for sustenance. Additionally, for the hummingbird to survive its yearly migration, it has to store a layer of fat equal to 1/2 of its body weight. What an interesting creature, and a great example of how animals have adapted to live at smaller scales.
Now, let's propose something a little bit different. Instead of our shrink ray, what if we could create an expand ray? This machine would have the capability to enlarge anything by a few orders of magnitude. So would very small organisms, such as insects or bugs, be able to live at our scale? What a frightening world that would be. Fortunately for us, though, insects couldn't survive being proportionately enlarged. Let's figure out why.
Insects have a very different kind of respiratory system than vertebrates. Rather than inhaling air, extracting oxygen in the lungs, and transporting it in the blood as we do, insects have a branched, tree-like network of tubes called trachea that extend through the body and open at one end to the atmosphere. This system allows oxygen to diffuse down the tubes, and it is very effective in smaller organisms. However, it doesn't scale up well because it is completely dependent on the diffusion of oxygen. At larger volumes, the surface area to volume ratio would decrease, and the insect's tissues would not receive enough oxygen to stay alive. Interestingly, about 300 million years ago, insects were significantly larger due to the higher partial pressure of oxygen in the air, which allowed for deeper oxygen diffusion. In current times, with lower oxygen partial pressures, this would not be possible.
Additionally, the ability for insects to fly is directly proportional to its wing area to volume ratio. If we were to enlarge a flying bug, its volume would increase at a much faster rate than the surface area of its wings. This would leave the bug unable to take flight. So perhaps the bug could just walk everywhere then. However, evidence suggests that this may not be possible either. As the organism is enlarged, its body mass will increase much faster than the surface area of its joints. This will place increasing pressure on these joints. Unless they can be made out of some very hard material in order to minimize wear, and also with good mechanical properties like diamond, giant insects wouldn't be able to walk around the earth either. At least when they are completely immobilized, they may be much less frightening.
As the climate of the Earth continues to change, we may see some slight variations in the anatomical makeup of different organisms. However, it does not look like we will be able to use our shrink ray or our expand ray without suffering some serious consequences. We can retire all of those ideas and focus on living our normal, respective lives at our normal scales.